Mass defect and binding energy. There was a lot of preliminary work we did yesterday with isotope notation and knowing what atomic number is and what atomic mass number is. I'm assuming you know that the atomic number is the location on the periodic table of the element or the nucleus or the atom, and it really tells you how many protons there are in the nucleus. So you should have your periodic table out, but I'm just going to refer to the one up here. When you take a look at boron, boron is atomic number 5. That means any boron nucleus or atom in the universe has to have 5 protons. It may have 6 neutrons, it may have 2 neutrons. That's not relevant to the atomic number. The atomic mass number is the total number of nucleons. So quick review here, if I gave you something like boron and I said it was boron 11, we don't need to write the 5, but to be complete, we would write the 5. The 5 is telling you there's 5 protons, that's the atomic number. The 11 is telling you in an indirect way that there are 6 neutrons, because the protons added to the neutrons has to give you 11. What we said, and I did a crafty job of sidestepping the reason why we even talk about this, other than to say it's necessary for explaining fission and fusion, which we'll get to later. What we said was if you could separate this out somehow into a series of protons and neutrons that are no longer bonded together with the strong nuclear force, if you could, and you don't, then what you would discover, what do we have? 1, 2, 3, 4, 5, 6, and 2, 3, 4, 5. I know I drew the symbol for the proton a little bit bigger than the symbol for a neutron, but that's not intentional. If you could do that, it requires a large amount of energy. And the reason it requires a large amount of energy is because that force that's holding those nucleons together in the nucleus, that strong nuclear force we learned about, is huge. So it's unimaginably big. Remember, the force between 2 protons in a nucleus, I think we got in the neighborhood of 920 newtons. Does that sound familiar? And that's the force required to lift 92 kilograms, which is over 200 pounds. That's at least 4 5-gallon water jugs. You can imagine trying to grab 2 in each hand and carry them. That's the force between 2 protons. And because energy and matter are the same thing, they just take on a different appearance, what happens is the mass goes up. It seems weird, but the sum of the masses of the parts is greater than the mass of the whole. It's not normally how things work, but this is how it works for nuclei. That energy required to accomplish this is called the binding energy, and the increase in mass is called the mass defect. So when the mass of the assembled nucleus is compared to the mass of the separate nucleons, they're different. The mass of the separated nucleons is greater than the nucleus. And I think we used an alpha particle yesterday, didn't we? Helium nucleus. Okay, so if I do this, the mass goes up. Why? Because I've added energy, and energy is mass. That increase in mass is called the mass defect. Okay, so however much the mass goes up by, that's the mass defect. And the energy required to accomplish that is the binding energy. And that's where we're at basically. That the energy in the system goes up as well, and that increase in energy is the binding energy. The only other thing you need to complete this picture is what's the relationship between the binding energy and the mass defect. That's the relationship right there. It's Einstein's theory of relativity. Delta E equals delta mc squared. Any questions from the practice problems or general questions? I don't want to spend too much time on general questions, but
I have a general
okay.
question. Is there like a certain amount of neutrons that it can gain or lose? Like obviously it can't have negative neutrons, but can an atom gain? Can it gain an infinite amount, or is it like?
I think what you're asking is if I pick on boron here, I said that we could have boron 11. And I think what you're asking is there a limit to the number of neutrons that can be added or removed and still have stable isotopes? And the answer to that is it's very complicated. And it may very well be the case, and I could look it up online, but it may very well be the case that boron 11 just doesn't exist. There might be boron 6, which would be a really weird one. I don't think boron 6 exists. Boron 6 would have 5 protons and 1 neutron to give us 6. There's a complicated mathematical connection between the number of protons and the number of neutrons and something being stable. And 5 protons and 1 neutron is an incredibly unstable arrangement. Usually, the numbers of protons are close to the number of neutrons, not like within 1 or 2, but if you take, for example, I'm going to pick on osmosium, or osmium, number 76. If I take a look at atomic number 76, and you can look on your periodic table, the atomic molar mass is given as, well, up here it's 190.2. On yours, it's probably very similar. Don't forget, that's an average of the different isotopes. So there might be osmium 190, osmium 193. But if you compare 190 to 76, 190 is a little bit more than double 76. And that's what you will usually find, is the number of protons and neutrons are very close, or there are slightly more neutrons. But there's, like I said, a mathematical relationship that predicts the stability. So it's not just pick any numbers you want. And that's why sometimes when I do this, I'll be honest with you, I wrote boron 11. I mean, I don't have a photographic memory. Boron 11 may not even be a stable isotope. It might not exist in the universe. Probably does, though. Okay. Other questions, specific or general? Yeah. 2A. All right. So we've got a carbon-14 nucleus, and there's a wealth of information when you see that carbon-14 nucleus, because you have your periodic table and you can look up carbon in case you've forgotten. It's element number 6. So when we see carbon-14, that's what we should think of. Right? Carbon is number 6. So that means that we're dealing with, in this nucleus, 6 protons and 8 neutrons. And I'm getting 8 by saying if there's 14 nucleons, 14 minus the 6 gives me the 8. You're okay with that? Okay. So what is the mass defect? What we need to do is compare this mass, which is the mass of the assembled nucleus, with the total of the masses of all of the pieces if I remove them. And this is where you're going to use the numbers at the top of your page. For a proton, 1.6726 times 10 to the negative 27 kilograms. And for a neutron, 1.6749. And those are given to you on exams. You don't have to memorize them. So I'm not going to bother to write down a whole bunch of numbers here. If I were to take 8 multiplied by the mass of a neutron, which is 1.6749 times 10 to the negative 27 kilograms, and add 6 multiplied by the mass of a proton, which is 1.6726 times 10 to the negative 27 kilograms. Just double check. I think I've got the numbers entered in correctly. What I get is if you could take that carbon-14 nucleus and just overcome the strong nuclear forces and just put everybody in their own little corner and add up all their masses, you would get this number. But this number is just a sliver more than the mass of the nucleus when they're all together. And the mass defect, by definition, is the difference between these two. I mean, one of the meanings of the word defect is kind of a flaw. And that's, I think, where it comes from. There's, like, if there's a defect in a diamond, there's a flaw. Well, here there's a flaw. Common sense says, I used this analogy yesterday, but common sense says if I take this paper and I do this to it, the mass should be the same, but it's not. Anyway, if I subtract from that the assembled nuclear mass, I will end up getting, the mass defect. Have I answered your question? Okay. You would then multiply by the speed of light squared, because E equals mc squared to get the binding energy, but you're okay with that now? Okay. Any other questions? Ian?
What do you mean when you say the mass increases? Because, of course, the amount of atoms and protons and neutrons and electrons are not increasing. What is increasing?
The mass of each particle. And I'm glad you asked that. And I've said this yesterday and I've said it before. When you have an increase in mass due to relativistic things like nuclear changes, it isn't that you normally think, like Christmas is coming up, my mass is going to increase. Okay? But that's because I'm going to eat more and I'm going to be adding more atoms and molecules in large amounts to my body. That's not what we're talking about. We're talking about keeping the amount of matter the same, but having everything with more mass. So in answer to your question, when I say the mass increases, you still have 14 nucleons in this example, but the mass of each, how about this? When these nucleons are separated, the mass of a neutron is 1.6749 times 10 to the negative 26 kilograms. Yes? Okay. If you could determine the mass of a neutron when it's in the nucleus, you would discover the neutron mass in the nucleus is less. So every single particle's mass increases by some value. It's just more massive. It's why, and then we're going to have to move on. It's why I've told you before that on your formula sheet where you have mass of an electron, it used to be that it said rest mass of the electron. That mass of an electron is the mass that the electron has if it's at rest, which is kind of a pipe dream, right? You can't get an electron to just sit there. Is that okay? Okay, we can maybe talk a little bit more because I have a feeling you have more to say. And that's okay, but we have to move on. Okay. All right, so we're going to move on today and look at radioactive decay. This would be on page 34 of your unit handout. Lesson 4.7. There are many types of decay. 3 of them are alpha, beta, and gamma, the first 3 letters of the Greek alphabet. This lesson is going to extend between today and tomorrow. And I never really cut it in half at the same point every semester. It depends on how things go. But I hope today to get through a comparison of alpha, beta, and gamma decay and to write decay equations for at least alpha decay, possibly beta decay. But we are not going to get to gamma decay today. We're definitely not going to look at what's called positron decay and electron capture today. We might discuss gamma decay in a little bit of detail, but not a lot. So what's going to happen is, once we write out what are called nuclear decay equations, we can apply mass energy conservation, and I'll explain what that means in a bit, to find out the energy involved during these processes that we're talking about. And we're going to end it today so that you're going to have some time to practice writing decay equations for alpha decays and also doing calculations involving mass energy. The name isn't important. You don't need to memorize this, but Henri Becquerel, a French physicist about 125 years ago, discovered radioactivity. And these are called forms of radiation, but this is nuclear radiation, not necessarily electromagnetic radiation. So when you go back to the previous unit and you talk about EMR, electromagnetic radiation, and you have that spectrum of radio waves, microwaves, infrared, visible, ultraviolet, X-ray, gamma rays, all of that, that's different than most of this stuff. But you'll notice that in that list, what did I just say at the end? Gamma rays. So I will tell you up front that gamma radiation, this type of radiation, is electromagnetic radiation, but alpha radiation and beta radiation is not electromagnetic. It's a different type of, quote, radiation. There's three main types that Becquerel discovered, and one of the first things that Becquerel did, being a curious physicist, is he passed these forms of radiation through a magnetic field. Now the magnetic field here, those dots, do I have the magnetic field labeled on your diagram with a B? I do? No? Well, we can put that on there. Be very careful here when I'm talking about this magnetic field that is out of the plane of the paper. That's not to be confused with the beta, which looks pretty much like a B. In fact, that's where we get our B from. I would like everybody to use your right-hand rule. All of these things, I'll just say they're things, are streaming left to right in the diagram, and the magnetic field is out. So I want you to use the right-hand rule to determine what the charge on that alpha radiation is. What is the charge on the things in the alpha beam? What is the charge on the things in the beta beam? I think it's safe to say that the gamma radiation, this is the symbol for gamma, the charge on the gamma radiation is non-existent. It doesn't have a charge because it's not deflected. And by the way, it's electromagnetic, which doesn't have a charge. Jack, are you with us? What's the charge on the alpha radiation if it's deflected down through a magnetic field that's out? Positive, good. So your fingers are out of the plane of the paper. If you're sitting at your desk, you're going to have to be holding your hand like this. The magnetic field is out. The particles are streaming left to right from your perspective. Positive particles are forced out of the palm of your hand. So the alpha radiation is positive. The beta radiation is negative. And that's what's concluded, that the gamma rays have no charge, the alpha radiation is positive, and the beta radiation is negative. You might make a little mental note here that when we put a detector at different places to detect these things, that we discover usually that the beta radiation is deflected through a greater angle. Okay, there's going to be a reason for that. So what's concluded here? What's concluded is alpha radiation consists of positively charged particles. You cannot have a positive charge unless there's something with mass. Something will only have charge, positive or negative, if it has mass. So the fact that the alpha radiation is deflected means it has a charge, which means it's physical particles. Okay? That's, I think, a significant idea here, at least in comparing alpha and beta. We're talking about particles, whereas gamma radiation is photons, it turns out, or electromagnetic radiation. But you already knew that. All right, we're going to talk now about the properties of these. The first property of all of these forms of radiation is they're ionizing. What does that mean for living things? Okay, possibly, hopefully not. Could be fatal. Why?
It causes cellular damage.
Which produces cancer. So these are cancer-causing, right? They ionize the DNA molecules which are all corrupt. And again, I'm not a biologist, so this is just kind of a cartoonish explanation. These grotesque DNA molecules that your body doesn't like reproduce themselves, and sooner or later you get a cell with all of that DNA in it, then it becomes a tumor, and that's cancer. So they're all cancer-causing. Now, what are the properties of these things? All of this information is in the chart already, but I want to walk through with you all of these things because it's not simple. First of all, you need to know what they are. Well, every single example that we have done in this course that says an alpha particle does this or an alpha particle does that, those alpha particles are the particles that are in alpha radiation. So when you look at that diagram that shows a stream of alpha radiation, it's just a whole bunch of alpha particles streaming away from whatever is emitting them. And it occurs to me now that I didn't really say this, but there's a radioactive sample in here. There's something that came from the Earth that's spitting this stuff out. It's naturally occurring. Beta radiation is a stream of high-speed electrons, and we're going to have to cope with something here. These forms of radiation could be referred to properly as nuclear radiation because they originate in the nucleus. That's what this part of the unit is all about, nuclear physics. They originate in the nucleus, and if you're even half awake here, you should understand that this is a bit of a problem because there's no electrons in the nucleus. So we're going to have to figure out what's going on there. Not right now, though. And gamma radiation consists of high-speed photons. Well, I shouldn't say high speed. How fast are the photons traveling? Speed of light, which is, yeah, it's a high speed, but it's the speed of light. Penetrability. Alpha radiation is the least penetrable. If I take alpha radiation and I have a detector. I have a detector here, which is a Geiger counter. That's what it's called. So I have a Geiger counter, and I take a source of alpha radiation, which is that little shiny piece of metal that's there, and it's a low dose. It's not, I mean, I'm not so sure I'd want to, I have to be respectful in handling this. I'm not so sure I want to put it in my pocket and walk around with it all week. And I want to be very careful, and we'll talk about this in a minute, so that I don't touch that gold foil, because I could potentially get some of the physical material that's emitting the alpha rays on my fingers. And then if I were to do something like rub my eye, it might get in my body, and then that material that's emitting that stream of alpha radiation is in my body. And that stream of alpha radiation, it's not this stuff that's hurting me, it's the alpha rays coming out of it, is going to just keep being absorbed by my skin and tissue, ionizing radiation, and it could produce cancer. But anyway, if I turn this on and I hold this, close to the Geiger counter, you hear some clicking. There's a needle as well. It doesn't matter. I can show you the needle. The needle is registering some level. So when you see those old movies, or like if you've watched the miniseries Chernobyl, they're walking around with a Geiger counter, and it's clicking, telling you that there's radiation present. If I put this here, and I take a piece of paper and put it between, it pretty much stops. By the way, this will click every now and then just on its own. There, okay? There's a few more. There's what's called background radiation. There's alpha rays, beta rays, gamma rays flying around us all the time in very low levels. So alpha radiation is easily stopped by something as thin as paper. If I were to take a look at beta radiation, and I guess I'll show you these. These are the sources. The dates on these are different because I have newer ones. The red is alpha, the green is beta. Now, I don't want you to get the wrong idea here. It's just beeping a lot because there's a lot of radioactive material in this. Okay? So I have a source of beta radiation, and there's a lot of it. I have a source of alpha radiation, and there's not much. This is like me having a big tub of ketchup and a little tiny mustard packet. Okay? There's just not a lot here. I don't want you to get the impression that this is always going to be the case, that beta is more intense. There are more beta particles coming off of this, a lot more per second. It has something to do with half-life, and we'll learn about that in the coming days. If I take a couple of sheets of paper and put it in between here, take some more paper and put it in between here, it's not changing anything. In order to stop beta radiation, you need a relatively, not dense, but you need some metal. I've got here maybe a centimeter of aluminum. If I hold this about a centimeter away and then slide this in between, it's pretty much damping out the radiation. So it's becoming harder to stop, which means beta radiation has more penetrability than alpha radiation. Gamma radiation, go ahead, Jack.
Is aluminum the only material that will stop beta?
No, it's a good question. Any metal, I mean, metals have different densities, right? So it has something to do with density and thickness here, but any metal, I would say if you had a roughly a centimeter, it would stop it. And this is what I mean by I don't know how far we'll get today because there are different discussions we could have. If I take a single piece of aluminum, this is just sheet aluminum that it's very, very thin. If I take a single piece of aluminum, it's not thick enough to stop it. So it has something to do with how much metal these beta particles are colliding with, okay? The beta particles go in and they collide with a few atoms here. It's not enough to bring them to a stop. But if they want to make it through 100 layers of this, then there's going to be more collisions. Ian?
Are they deflecting like the Rutherford experiment?
No. They have so much energy, and even the alpha radiation, don't confuse the collisions with the alpha particles and the atoms in the paper or whatever. Don't confuse those collisions with the gold foil experiment. Okay? The energy of these alpha particles or beta particles is scads beyond the energy of the alpha particles in Rutherford's experiment. It's not entirely true, but I think that's the easiest way to think of it. Don't confuse the two things. Okay? Gamma radiation will not be stopped by a centimeter of aluminum. So this is gamma radiation. Again, it's not clicking as often as the beta. It's clicking more than the alpha, but that just means there's kind of a medium amount of material that's in here. And I don't know if you can see it on this photo, but do you see kind of a hazy spottiness here and here? That's the radioactive material, and it is encased in plastic for my protection. This silver piece of metal is the piece of radioactive material producing alpha radiation, but it is not encased in plastic for my protection. You can see it, and in fact, in this one, you can see it's just taped on there. Why isn't this alpha source behind plastic to protect me? Well, the radiation would be stopped. It's stopped by paper. So as a teaching tool, and that's what this is manufactured for, as a teaching tool, if it was encased in plastic, they might as well just give me a poker chip and say there's something radioactive inside, right? It can't be covered up. But I go back to the gamma, which is the orange one, and I put the aluminum in here, it's not affected. So what's required to stop gamma radiation is, a meter or two of concrete would do the trick, or if you want to have the density needed to make this happen, you use something that's very dense like lead. And the reason I'm putting the gloves on is because I have to handle lead, and lead is what's called a heavy metal, not the good kind, not like Black Sabbath. It's a metal that if it gets in your bloodstream, you get very ill. It can kill you. This is lead. It's about 1.5 centimeters thick, so in order for me to make sense of this, I can't put this a centimeter close away from the detector and then attempt to slide this in. So if I put this lead here, it's stopping a lot of it. Well, it's stopping some of it. I'm looking down. I want to adjust the scale on the needle. I'm looking down at the reading on the needle, and it's at 1,200 counts per second, which means every second 1,200 photons are leaving this and passing through Brody. Okay? How do you feel? Okay. Takes a couple hours to really affect you, so you might be a little tired this afternoon. I'm just kidding. It's not going to affect you. The energies here are for educational purposes. They're very low, okay? But, yeah, about 1,200. I put this in, it immediately drops to about 800. So if I really wanted to stop it, I would need lots of lead So I have some lead folded up here. Lead's a very soft metal. Still not 100%, but it's certainly diminishing it. So you need to know about the penetrabilities of these things. The other thing you need to know is the relative harm that they can do biologically to humans or animals. And there's a huge misconception out there. And it's just so much so that when they ask questions about this next bit of business on a diploma exam, 80% of the province gets it wrong. And I chalk that up to just, it's such a big misconception that people are teaching physics and they got it wrong. You would think that because the the gamma radiation is the most penetrable, that it has the most energy, and that is true. But you would think because the gamma radiation has the most energy, that it would do the most damage, and it turns out that's not true. Okay? Alpha radiation is easily stopped when it hits your skin. So if I have alpha radiation next to my skin, all of those alpha particles are being stopped. And it's the process of stopping the particles that bleeds the energy out of the particles. And that energy that leaves the particles is what does damage to your skin or your cells. So we estimate that an alpha particle in being stopped by your skin is stopped within about 1 millimeter of skin. And tens of thousands, potentially tens of thousands of collisions between that alpha particle and molecules of your skin happen in slowing down and stopping that alpha particle. Okay? And each of these collisions damages tissue, damages DNA, damages cellular structure. So there's, in a very tiny, tiny layer of your skin, a lot of damage that's close together. So if you, an example I can give you is if you were working in a lab that had nuclear material and you were not following safety procedures properly, and there was some alpha radiation, I shouldn't say alpha radiation, there was some material in dust form floating in the air that was an alpha emitter. And you walked by and went, and it went into your lung and it lodged itself in a cilia on your lung, on the inside of your lung, then it's going to sit there continually emitting that alpha radiation over time. Every second of every day, alpha particles are going to be damaging more cells in that region. And that's going to lead to cancer. So on the other side of things, gamma radiation is harmful in high doses. I mean, if you're exposed to a very, very high concentration of alpha radiation in a short period of time, the person may be dead in hours. Like it will happen that quickly. Within an hour or two, your tissues and your organs will be so damaged they can't function. You'll start bleeding internally and you'll die. Okay? And there's no real cure for it. But individual or small levels of gamma radiation don't cause high levels of damage because they just go right through you. They go through you so fast at the speed of light that they maybe collide with a couple of atoms, and they don't do a lot of concentrated damage. On the other hand, beta radiation is, kind of the middle ground. It's not as simple as saying more energy is more damage. Okay? It's like watching one of the Die Hard movies, I don't remember which one, and there's a bus going down Park Avenue or someplace in New York, and they have all these cars parked there, and the bus is just flying. The bus hits a vehicle, slows down, hits a vehicle, slows down, hits a vehicle, slows down. By the time it gets to the end of Park Avenue and they're showing the scene, there's a lot of damage, isn't there? Right? But if somebody stood at one end of that road and fired a bullet, it might hit one or two cars, making a little hole. I mean, that's just an analogy. It's not perfect. So any questions with the properties of these three types of radiation? Yeah.
So for producing them, like if you get
Well, that's a great question. How long does it take before it burns out? You will notice that and I'm not going to set it up again, but the alpha radiation did not click a lot. There weren't a lot of alpha particles. You're in math right now. No. Last year? You haven't taken 30-1 yet. Okay. If you look very carefully, this is polonium-210, which is the isotope of polonium that's producing the alpha radiation. This is just a photo of the front, and this is a photo of the back. You'll see that this says May 2013. And if you look carefully, it says 138.4 D, and that's the half-life. 138.4 days is the half-life. And we're going to learn that what happens is, after every 138.4 days, you will only have half of the radioactive isotopes still there. Half of them will have fired their bullet, fired the alpha particle out, and become more stable. Okay? If you take something and divide it in half, even 10 times, you will have next to nothing left. I don't want to do the math right now. We'll do that day after tomorrow. So the general rule is if you go past about 10 half-lives, it's fizzled out or burned out in your words. Okay? I actually have a whole container of these things. The first year I taught here was 1997, 98, and I have one that's stamped 1998. Well, it's useless. I hold it in front of a Geiger counter, it doesn't do anything. And about every 2 years, we have to purchase some more. Without taking this out, Annalee, the alpha radiation is this bottom one. What is the date on that?
May 2020.
May 2020. Well, let's just take 2 years, which is about 730 days. What's 730 divided by 138? Got to be 6. So I don't know. 5.5-ish. Okay, so that's 5 half-lives, and already it's weak. I'm not saying a brand new one would be clicking away like the other ones, but it would be a lot more active than the one I have. On the other hand, the strontium-90, which is the one we use for beta radiation, has a half-life of 28.8 years. So that's going to be around. I'll be retired. I'll be long gone in every way, and this will still be ticking. Okay. This is about 5.27 years. Have I answered your question? Okay. It's just a matter of how much fuel there is there before it fizzles out or burns out. Any other questions? Ian?
It's the stopping of the particles that are damaging and not the going through the cells?
Yes. I mean, don't get me wrong. It's all... We've all watched movies with violence in them, so I don't feel bad talking about this. It's like in a movie, somebody getting shot and the bullet is stopped by them. All of the momentum and energy of the bullet is transferred to the body, doing a lot of damage to the tissue. But you'll often hear in movies, oh, no, you'll be fine, it went right through. Well, that's not necessarily the case, but if a bullet goes through you, your body doesn't take away much energy in slowing the bullet down. The bullet slows down a little bit. And that means that not a lot of energy is used to damage your tissue. I mean, don't get me wrong. These are all analogies. If a bullet even grazes the right part of a human anatomy, you could be in very serious trouble, right? I mean, you can come up with your own analogies there. But yes, it's the stopping. Any other questions? Yeah.
Is the rate of radiation directly connected to what type of particle it is?
Yes. In fact, the rate of radiation is related to the half-life. So, and these are really good things. Everything we're talking about here, nothing so far is something that I would go, oh, you don't need to know this. You need to know this, that if you had a half-life of 2 days, I would rather stand next to something with a half-life of 20 years than stand next to something with a half-life of 2 days. all other things being equal. Because the half-life of 2 days means it's going to fizzle out quicker, which means it's going to be, whereas the other one that has a half-life of 20 years is like, relatively speaking. So the smaller the half-life, the more readily it burns out. But in burning out, it's emitting all of the particles that it can to burn out. And we'll learn in a minute that when this polonium-210 undergoes alpha decay, it's no longer polonium-210. It's something else that's stable, that does not emit these dangerous things. Any other questions? All right, so now let's get to the kind of the operational part of this by writing decay equations. But I want to take a minute here and go through some things that we need to know because you just might be asked, and some things that you need to know in order to do the physics. First of all, I've always disliked the word equation here, but in chemistry, if you write something like I'm not going to worry. Well, I'll balance it, I guess. When you have something like this in chemistry, and everybody's taken some chemistry, you took Science 10, this is called a chemical reaction, but what we write is called a chemical equation. I don't know if, say, Miss McFeely really stresses that, but this is called a chemical equation. It's not a mathematical thing, but it is an equation. It's saying that this stuff on the left turns into the stuff on the right. And by the way, in a chemical equation, there's something that's conserved. Atoms. Atoms are conserved. You have a total of 2 oxygen atoms on the left and 2 oxygen atoms on the right. And I'm not going to explain balancing or chemical coefficients or anything like that, but you've seen this before. Okay. Well, not atoms, but instead other things are conserved during nuclear changes. Momentum is always conserved. You can never have a nuclear change where momentum is not conserved. In other words, it will always be in an isolated system from Unit 1. But energy is not conserved. And this, by the way, is the whole point of nuclear changes. The energy is not conserved. When that alpha particle comes out of the polonium-210 or whatever it was, it has kinetic energy. And I will tell you right now, that when the alpha particle was part of the nucleus, that energy didn't exist anywhere in the universe. Energy is created during that nuclear change. However, there is something that's conserved, which is mass energy. And we will delve into this in baby steps. But basically what this is saying is the mass can change as long as the energy changes by an equivalent amount. So we can lose mass as long as we create energy. Remember my analogy of the ice and the water? We can lose ice as long as you get that much water. You can lose mass as long as you get that much energy. The other two, which are very important in balancing these equations, is charge is conserved and atomic mass number is conserved. And with that, even though we haven't used them, I think on your formula sheet, I think that's all 10 physics principles. There should be nothing on your formula sheet that you have not heard of under the physics principles section. I mean, we don't know how to use conservation of mass energy, and we haven't really talked about conservation of nucleons, but we're going to do that part right now. So we use these last 2 ideas to balance a nuclear equation. For the examples, you're going to need your formula sheet. Maybe you won't need your formula sheet, but you're probably going to want to have your formula sheet. You'll definitely need your periodic table, a calculator, something to write with. What happens during alpha decay is 2 protons and 2 neutrons, which is the structure of an alpha particle, are kicked out of the nucleus. Okay? That's what happens. And they are kicked out in the form of an alpha particle. Why? Listen, the answer to why this happens is the answer to why anything in the universe happens on its own. Because it becomes more stable. Why does water flow downhill? Because it's more stable at the bottom of the hill. Why does that barn that I pass on that old abandoned farmland every summer and driving up to the cabin, why is it a little more and more decrepit and crumbled? Because it's becoming more stable. What we're talking about here for things that become more stable are exothermic. And I just want to quickly see if I can make a connection between chemistry and physics. If I take a piece of sodium, have you seen the sodium in water experiment demonstration? If I take a piece of sodium, and if it were a chunk of sodium the size of my thumb and I want to put it in water, I'd want to stand back and throw it in the bucket of water. It's an immediate reaction where that sodium reacts with the water to produce sodium hydroxide and hydrogen gas, and there's so much energy released, the hydrogen ignites, right? You've seen that explosion in chemistry? Well, little. It's probably a little, but you've seen it. That's exothermic. That happens on its own. Anything that is exothermic that happens naturally, like all of these emitters, and I've misplaced my radioactive sources, there they are. All of these emitters, this is happening on its own, it's exothermic. So these all happen to become more stable. The arrangement of the nucleons without those 2 neutrons and 2 protons is just a better arrangement. It's more stable. During alpha decay, there is a decrease in mass, and I'll talk more about that in a second. The symbol for an alpha particle is that. Think about what that's telling you about protons and neutrons. Darius, how many protons? 2. Why are there 2 protons looking at that notation? The bottom number's 2. So that's helium, and helium always has 2. How do we know there are 2 protons? Caden?
Because it's the same number as the atomic number.
Okay, and how do we know there's 2 neutrons? There happen to be 2 neutrons as well. Carly?
Because if there's 2 protons and 2 plus 2 is 4, which means that there's 2 neutrons.
Right, this is the number of protons and neutrons. So it would make sense that you take the total atomic mass number, which is 4, and subtract the atomic number, which is 2. So there's 2 protons and 2 neutrons. Darius made the point that this is helium, and we could certainly write helium, but we would probably write alpha particle. You could write helium. Okay, here's the first example. Write the decay equation for the alpha decay of radium-226. We have to start off by determining what radium-226 is in terms of its symbol and in terms of the number of protons. I always confuse radium and radon, but I think radium is a symbol Ra. It's on near the left-hand side. Where is it? Radium-226.
It's 88.
Yeah. So it's on the left-hand side over here beside francium. I can't move this thing down right now. So it's number 88. And it's Ra. So what happens? An individual radium nucleus is sitting there, minding its own business, and by a random chance, a particular nucleus spits out an alpha particle. Now, what will we have left? I told you just above this that the total number of nucleons must be conserved. How many nucleons are there to begin with? Well, there's 226. Right? We've got 226 nucleons before. I hope this is obvious, but I'm just going to put before here. And this is after the decay. But if you have 226 before, then you need to have 226 after. And we only have 4 accounted for. So Brody, how many more do we need? 222. It's just a matter of saying the numbers on the top have to add up left and right. So 222. Now, the bottom number is protons, but more importantly, the bottom number is charge. Protons are the only things in the nucleus with charge. So what this 88 represents, I know it represents 88 protons. We know that. But more importantly, what it represents is 88 elementary charges that are positive in nature. That is not an electron. That is the symbol for the elementary charge. The total charge before is 88 times 1.6 times 10 to the negative 19 coulombs. Okay. That means we need a total of 88 after. So I just want to point out to you that I would really prefer for you to think of this bottom number. I would prefer for you to think of this bottom number not as protons, but as charge. That will be helpful later. So if we have a total of 88 positive charges before and after, we only have 2 positive charges in the alpha particle. Ian, how many positive charges do we need more beyond that 2? 86. So that means that when radium-226 undergoes alpha decay, we get, and you look up on the periodic table what number 86 is, you get radon-226. So if I had a radium-226 alpha source, and mine's polonium-210, when it fizzles out, it will no longer contain radium-226. All of the radium-226 nuclei will have changed to radon-222. The next question is, use the listed nuclear isotope masses to find the energy released. Well, let's just explore something here. I would like everybody to find the total mass before and the total mass after. And let's start by doing it in atomic mass units. So the radium-226, the mass before is that. There's nothing to calculate here. It's 226.025410 atomic mass units. I would like everybody to find the total mass after. Afterwards, we have the radon-222, and we have the alpha particle. This is interesting because Darius said helium. Well, I've got helium-4 up there, which is the mass of an alpha particle. I don't particularly feel like carrying numbers this morning, so Will, can you tell me what you get?
226.
Little louder, please.
226.020181.
Anybody else up for that number of atomic mass units? Okay, so what has happened here? We've lost mass. There's less mass. And it's not, I'm not trying to be snarky or sarcastic here. It isn't this. It isn't we've lost mass. Everything is still accounted for. We still have the same number of particles. We still have the same particles themselves. It's just that everything is less massive. And what that means is that the ice has turned to water. The mass has turned to energy. And if we find the change in the mass by taking the final mass minus the initial mass, and we can still do this in atomic mass units for the time being. What is it we get? How did I do there? Yep. 0.005229 atomic mass units, which means that, and I'm sorry, we do not get that we get negative, don't we? That's important. It's very important. So we get a loss in mass because the change in the mass is negative. To find the release of energy, the change in energy, we can use Einstein's relativistic formula. The change in energy is the change in the mass times the speed of light squared, but we have to work in kilograms, right? This formula will only work in kilograms, so you need to take now that number of atomic mass units and multiply by how many kilograms one atomic mass unit is. Which, I mean, you probably remember, but it was only yesterday that I introduced you to that. It is on your formula sheet. And I get that. So my change in energy will be the negative 8.68 times 10 to the negative 20. I'll just check that out to confirm this in a second. Bless you. 30 multiplied by the speed of light squared. We all know what the speed of light is. I don't think I need to write it down. And we'll get an energy. So this is our delta M. I'm putting the negative back on because I think it is important. I multiply by the speed of light squared. This is the energy change. This is one emission of an alpha particle. This is one radium-226 spitting out one alpha particle. And that's in joules. I asked a similar question yesterday. Is this a lot of energy? And everybody yesterday said no. How are you going to answer that today? Yes. How many electron volts is it? That's kind of the measure. There are 1.6 multiplied by 10 to the negative 19 joules per electron volt. Are we in the millions? 4.88 million? Yep. EV. Who's in chemistry 30 right now? Okay. So in chemistry, you don't use delta E, you use delta H, right, for energy? What does a negative delta H mean? It's exothermic. Exothermic, I don't know how much this is stressed in your chem class, but exothermic changes are always naturally occurring, spontaneous. In redox, your spontaneous redox reactions are exothermic. And that leads to the answer to the final thing, which is where we're going to stop. Why is the mass of the products always going to be less in a radioactive decay? The answer is because it's exothermic. And the energy has to come from somewhere, and it comes from matter going away and energy taking its place. So I just want to finish this by saying exothermic, in terms of nuclear changes, will always be matter changing into energy. And that energy is used to carry off the alpha particle. Where's the matter? It's gone. Where is it now? Energy instead. That's what we mean by mass energy conservation.